Hey, cheers guys. Thanks for having me here. Thanks to CoinScrum and also to KR1 who have been really supportive and helped make this a really productive trip. Really awesome to be in London, back in the mother country. I'm from New Zealand, so it's a long flight. But I want to talk today about Dfinity, obviously. I'm going to move quite quickly. I want to explain basically the context, the market positioning of Dfinity, or the problem that we're trying to solve. And we generally call that Cloud 3.0, which is a nice little bit of buzz phraseology for you there. Then I'll dive right into some super technical stuff with threshold signatures, threshold relay, and probabilistic slot consensus, which is essentially our consensus system. It's a bit of this is very experimental. I've never really explained this stuff publicly, or I haven't given this presentation before ever. Dom loves to talk about threshold relay, but it's such an arcane and bizarre and kind of technical subject that, I don't know, we'll see how successful we are. But diving right into Cloud 3. So it's quite fashionable to use this moniker of third generation, right? Third web, the Cloud 3, what have you. And it's based around, or it comes from this idea of three different ages of the internet. The first being the protocol age, the 80s and 90s, when we had the dominance of TCP/IP as the primary building block of applications. It was a time before the web or the internet had matured to become this e-commerce platform that happened at the beginning of the 2000s with the end of the dot-com boom. And really it was that pitch of the dot-com boom, the idea that you could have one storefront to serve the entire world, that sold people on the idea of the internet as a place to do business. And it drove this huge amount of investment into internet companies and into businesses built on top of the net, and into basically creating services for these companies. And that led to the emergence of Google and the proliferation of services like Amazon Web Services that turned the internet from a fully democratic, fully egalitarian space into something that was a product, kind of a B2B product that was sold by Google and Amazon and eBay and Facebook to businesses so that they could better reach consumers. And it's really not in the vision of Tim Berners-Lee, the guy who originally conceived of the World Wide Web. So what is this third generation? Well, it looks like protocols that behave like the platforms that were built to serve these new e-commerce businesses. And that is really the dream of kind of Ethereum. It's the dream of all of these other competing blockchain platforms, Polkadot and Dfinity, Cardano, and the rest of them. And if we can use blockchain to fill the role of kind of Google and Amazon as kind of a business logic as a business logic service, then we can fundamentally change the way that the internet works. So what's wrong with information technology today? Well, you've got vendor lock-in, inter-version and inter-platform compatibility issues. That means that if you update a piece of software, it might not be compatible with the previous version. If you update, if you have the Microsoft version, this is kind of a bit of a throwback example, but a Microsoft version, it might not be quite so effective, or it might not be perfectly interoperable with a Windows version of a product. It's labor intensive to support IT systems, and inevitably there is some downtime, as we saw with the massive Amazon S3 crash last year. And there are tremendous privacy and data security issues that we don't even need to come up with examples for that right now. What we should be able to do is totally rely on our on our internet services. You know, there should be zero downtime. This stuff is a machine. It should be able to run itself. It shouldn't be complex. We should be able to remove humans from the equation. 90% of leaks or 90% of security compromises come from the interaction between humans and IT services. So if we can get humans out of the picture, we don't have to worry about the same degree of, or the same frequency of security breaches. There should only be one version of a product or of a piece of software, right? A hammer should be a hammer. You don't want to have multiple versions of a hammer, right? You don't want to have this. We've become used to a situation of endless iterations of software, but we're also required as users of that software to participate in the updating of or the migration to new iterations. And that should all be taking place on the back end. And of course, we should have perfect privacy and total data security. So the idea of the next kind of generation of software architectures is basically going to be an application living on your phone and your data and the logic of the application stored in the cloud and served to your phone or your computer when needed. This is essentially what Apple, Google, Microsoft, and the Mozilla Foundation signaled when they developed WebAssembly. And WebAssembly is essentially a virtual machine that runs in your browser that's a compile target for any any programming language. That could be Python, Go, Haskell, which lots of people seem to be very fond of Haskell in this space, JavaScript, whatever. The idea is that you should be able to run any software whatsoever in your browser using the WebAssembly virtual machine. And in August, I believe, of 2017, the WebAssembly project was completed, and now all of the browsers produced by these internet giants all feature the WebAssembly virtual machine. We think that rather than hosting software in a centralized cloud, we should be able to store that. We should be able to store that code and that data in a decentralized cloud, and that is the dream of Dfinity. And not only do we want to store that code and that data, we also want to be able to run some of those applications in the cloud. So if we think of Amazon Web Services, we can imagine that would be tremendously helpful, or Google services as well, for tremendously helpful for running high performance software, right? You could do it on your laptop, but you're limited just by the virtue of the form factor of the hardware itself, whereas there's no form factor limitation in the cloud. But we know that there's this massive problem with performance of blockchain computers, and so the idea is we need to scale this stuff, and we need to improve the performance of decentralized world computers like Ethereum, and that is the holy grail of blockchain, as we all know, and that's what Dfinity is going after. So just to recap on the two different models, we have an incumbent model that's led by this oligopoly of service providers. It's complex to run services in the cloud today. There's human-based security, which is behind all of these security leaks. You only get 99% uptime, so that one day in 1,000 when your service goes down could be a very, very critical day. And we have to pay for DevOps. So there's the additional expense of having to pay people to manage your IT infrastructure. Whereas the beauty of Dfinity, or any world computer, we're defining the opportunity here, is to create a decentralized rather than an oligopolistic protocol. It's monolithic, so it's not complex. You upload your software and you can forget about it. It's perfectly secure, 100% uptime and self-maintaining, so you don't have to worry about DevOps or people getting involved. How do we actually do it? Well, it's essentially an iteration on proof of work, which we all know has been phenomenally successful behind Bitcoin, and it's still the backbone of decentralized blockchains today. But it's just not scalable. And what proof of work gives us is two things. One is randomness, and the other is an economic disincentive for Byzantine behavior or misbehavior. And the way that we solve this problem is using a scheme called threshold relay. But to really understand how threshold relay works, we need to understand threshold signatures. So I'm just going to give this a shot because I've never actually explained this to a group of people before. So the idea of a threshold signature is that you have a whole bunch of pieces of a private and public key pair. So who here is familiar with public-private key cryptography? Some people. So the idea of public-private key cryptography is that you have a public key that can be used to verify a message or verify a digital signature, and you have a private key that can be used to create that digital signature. And because there's this asymmetry between the two keys, we know for a fact that someone who has presented a signature and along with a piece of data, we can use the public key to verify that they did indeed have that secret private key that signed that data. But the beauty of threshold signatures is that we can split this up. So we can require that a number of parties sign with a private key in order to create a verifiable signature. And the way it works is we use a distributed key generation algorithm to generate key pairs across a number of computers. So that could include up to, and in the case of DFINITY, 400 different key pairs get generated, or different key pair shares. And then everyone shares their public key, which is used to validate a signature. So that, because that's shared, that becomes public knowledge. And everyone has the ability to validate what is signed by the private keys of this group. What they do is they collectively sign pieces of data and publish those portions of those shares of the signature. And those shares of the signature can be assembled into a whole signature. But you don't need all of them. You only need a certain portion. So it's a lot like, say, having a committee. Say you have a jury that is elected to make a decision of some sort, say on a court case. You could use something like a threshold signature scheme to enable just a handful of participants, just say or everyone can vote, everyone could choose to sign an output or sign a decision, and you could assemble all of the signatures, and provided you had a majority, that would give you enough to provide a complete signature that is verifiable with the public key. And so what I'm trying to explain really is that this each piece of these private keys, each private key can produce a share of the signature, and provided you can come up with a majority of the signature shares, you can assemble a verifiable signature. And that enables us to do some really, really interesting things. So what we do to generate randomness in DFINITY is we start with any arbitrary source of randomness. This could be a dice roll, this could be someone's mother's maiden name. It doesn't matter, it can be predictable, it can be known to the world. We then use that to randomly select a group of what we call a notarization committee from the DFINITY miner base. That notarization committee then generates a threshold key pair and signs the original piece of randomness. The signature that emerges from this signing process can then be used as a source of randomness to select the next the next notarization committee. And this process can repeat. That next notarization committee can then re-sign that previous signature in order to continuously create randomness that can be used to reselect subsequent committees. And the beauty of this is it's fully unmanipulatable, it's fully deterministic, fully unpredictable, and this kind of tamper-proof, deterministic and verifiable randomness can be used to power all kinds of scaling solutions that allow DFINITY to perform. What we can also do is we can use these randomly selected committees to sign blocks. And you know, it's a phenomenally simple process because we're already gathering these randomly selected committees that no one could possibly predict the membership of. We can also use that as a way to sign blocks in the same way that Bitcoin randomly selects a network leader by running a brute force problem. The problem with that is that because these blocks inevitably proliferate through the network via a gossip protocol, it's very simple or it's inevitable that eventually some blocks will receive full signature, full threshold signature status simultaneously, potentially conflicting blocks. So we need to have a way to determine a canonical version of events or a canonical history. And so the way we do that, quite simply, is because we're using proof of stake in order to participate in the DFINITY network, all miners must first register. That's naturally part of a proof of stake protocol, DFINITY being proof of stake. And because they register, we know who's going to be part of the validation process in advance. We know who's going to be producing blocks. Again, in proof of work systems, we don't know who's going to be producing blocks. And so because of that, because we do know who is, we can essentially rank these miners arbitrarily using the random beacon. And so in the case where there is two different blocks that receive full signatures, we choose between them based on arbitrary ranking of the miners using the random beacon. And that's the magic of DFINITY's consensus system and our reliance on randomness. And right now we actually have full consensus running on a testnet internally. It's a production testnet, but unfortunately the GIF wouldn't play on the PowerPoint. So I have this demo from last year when we just had a very it wasn't quite as advanced as it is today, but it gives you an idea of what is possible with when you have this system running. So what we can see here is the continuous random selection of nodes that are participating in this notarization committee, and the large circle that you see moving around rapidly, that is the miner that is selected to lead the network in any particular round. And obviously we don't necessarily need to rely on selecting a leader, but this just gives us the option to make sure we don't ever have forks. In this, the average block time in this demo is half a second, which is really just network traversal. And I mean, we're going to down tune the network when we launch, which will be to probably 3.5 seconds per block. We can also reliably say that we have 2 block finality. So in this demo, 1 second finality. In the production network, because we're going to slow it down, it'll be 3 second finality. But again, just phenomenal advancement, all based on the fact that we have reliable randomness. And so just to review, we're entering a new age of software architecture. The cloud is going to be at the absolute heart of application design. DFINITY can offer a more secure and less expensive alternative to large centralized cloud providers. And the reason for this is the security and the lack of a need for a support team, the lack of need for DevOps. So even though we know that we have all of the inefficiencies of a decentralized architecture and an open architecture that is exposed to attack from all sides, we also have this phenomenal reliability, and we don't need to worry about maintaining that system because it's built to be resilient from the start. And at the heart of Dfinity, and I believe that this is at the heart of all future or any successful decentralized world computer, is WebAssembly, because we have this shelling point around it with Mozilla, the Mozilla Foundation, Apple, Microsoft, and Google. Blockchain, because we all know just the sheer resilience of that data structure, and threshold relay, because randomness is just one of the most important elements of any ungameable system, of any secure system. And threshold relay is probably the most efficient way to get that. And if there is any other way, it's probably not sufficiently more efficient for it to be effectively, for it to have an effective diversification of service. And that's Dfinity. So happy to answer any questions if you've got them. I mean, Dfinity it's very similar to Ethereum, EOS, Cardano, but it's just that we have a more resilient, we just have more resilient consensus.
So ICO before or after the product?
We did an ICO. Yeah, we did an ICO in February of last year.
Oh, okay.
For 4 million, for 3.5 or 3.9 million Swiss francs.
Oh, okay.
So we haven't worked out anything to do with the token, the Dfinity token. Right now we're entirely working on the actual underlying, the protocols themselves. The token will be used as it's a proof of stake network, as they call it. I don't think that's a good term. I think it's a popular use term. I think a better term is a bonded validator system. So you have to post a bond. That bond has to be in a network, in a protocol token. So it's very much like a proof of stake, any proof of stake system. Only, I think we're going to probably have a minimum required bond, but we may not reward based on the sheer number of tokens that an individual has, or that a single node has. We may just offer a set reward per node. But I don't know, we haven't worked it out yet. We do have another system that is that I haven't talked about at all, which is an internal governance system. And you'll also be required to post a bond to participate in the governance. Then also you'll need to pay fees, and that will be in the native Dfinity token. So this is actually a point of, a good point for discussion, because we don't really know how this is going to play out. But inevitably, I mean, what Google, Microsoft, Apple, and the Mozilla Foundation's investment in WebAssembly indicates, and what we can imagine from just looking at reasoning about the performance limitations of a device that's in your pocket versus a data center, we're going to see the outsourcing of things like storage and high performance computation to data centers, and instead a reliance on the latency and the bandwidth of the connection to the device as a way to mediate that relationship. So I think we'll see applications will have pointers to the information itself stored in a data center, and then that say the UI might be served to the device at the time that the application is opened, And if that application has been updated, because everyone's referring to this canonical instance or this central instance, there's never a need for the user to ever update because the application that is behind that address updates on its own. And this is what, or, can be updated centrally by the developers themselves. Well, I mean, if the network was centralized, then registration could be refused. I mean, that's the whole idea, is that this is an open network, so the network can't refuse registration. As for a participant, to participate, you need to place a bond. Just like, say, if you want to get a flat, you've got to put up a bond. You've got to register the fact that you're going to be in the flat. You can't have a flat without actually registering as or getting on the lease or whatever. So to participate in any proof of stake system, you need to register. Well, so it's just the block time, right? So read is always unlimited on a blockchain system. Like blockchains are great for read. You've got totally unlimited performance, right? You've only got limited write performance. So the only time when you have a problem with latency is when someone's actually making a payment, and we get, in our production network we'll have 7-second finality.